Dymola is capable of simulating dynamical systems over a wide range of domains, including mechanics, electronics and thermofluid analysis. The package browser to the left shows all the available building blocks. Looking inside the fluid package, we find models for vessels, pipes, machines such as pumps, valves, and fittings such as T-junctions and bends. There are also boundary elements, to define prescribed flows, pressure, temperature, and so on. Now, let's build a simple fluid transport system using Dymola's built-in components. We begin by navigating to the fluid package. Components are inserted through a drag-and-drop maneuver. First we insert a system component, which is needed to define the strength of gravity. Next, we will add a tank which holds a fluid. We can easily manipulate the size and position of a component icon. By double-clicking on a component, we can set its properties. Here, we set the tank's height and area, and its medium is set to water. A medium is chosen to assign properties such as thermal conductivity, density, and heat capacity. Now, let's insert a mass flow component, to model water being pumped at a given rate. We change the component's name to inlet. The inlet is also given a constant mass flow and temperature, and its medium is set to water. We will connect the tank to the inlet by means of a pipe. Icons may be rotated for visualization purposes. The pipe is intended to be vertically oriented, and we will let the icon stay as such. As with the tank, the pipe's properties may be set after double-clicking its icon. Here we specify its length, diameter and static pressure head, while setting its medium to water. Let's now connect all of the current components. To connect two components, we select a port on any component, displayed as a circle. The connection is finished by dragging it to another port. We will add an outlet to the model, using the boundary class. The boundary component is renamed to outlet. For this model, we specify a constant pressure and temperature, while setting the medium to water. When entering a quantity, we may choose the unit in which to specify it. Unit conversion is conveniently handled by Dymola in the background. There is also support for custom user-defined units. We will include a valve in the model. After adding the valve, we rotate its icon, and we then edit its properties. Here, we set the nominal mass flow and pressure drop, in addition to setting the medium to water. Now, we connect the outlet, valve, and tank, in the same manner as earlier. The valve may be open or shut, and its state is controlled by a Boolean signal. We will use a constant Boolean signal for this example, represented by a Boolean constant component. We connect the signal block to the valve's input port, and double-click its icon to edit its properties. With a constant false-valued signal, the valve will keep closed. The last thing to do is to define properties for the tank's ports. Although it's not clearly visible in this diagram, the valve and pipe are connected to two different ports on the tank. This interface lets us define how many ports the tank should have, on what height they are to be located, and their diameters. We will use two ports at a height of 0 meters, relative to the tank. The model is now ready to run. But first, let's save our work. A model can be saved just as any other file. If we desire to examine a component more closely in the model, we can do so at any time. Open class takes us to a diagram view of the component. While viewing a class, we can conveniently switch to its coding layer or its documentation to retrieve desired information. By using the tabs feature, we can instantly return to viewing the model. So far, we have demonstrated how to build a simple model with constant inputs, though Dymola supports general expressions which depend on time and state variables in a model. This pipe network is an example of a more complex model, retrieved from the examples library included with Dymola. Let's go back to our model to simulate it. We will switch to the Simulation tab, and then enter the simulation settings. We will set the simulation time to 10 seconds. From here one may also change the solver algorithm and solver tolerance. We now simulate the model using the Simulate button. Now that the simulation is finished, we can visualize the system history using the animated diagram view. As we play the animation, note how the water level in the tank changes. In the browser on the left, the components of the model are listed. Expanding an item shows all quantities associated with that component. By checking the box next to any variable, it's included in a line plot. If we plot the flow of mass through the valve, we observe that it is 0, which is expected since it's shut. By checking another box, we could plot the pressure drop over the valve, for instance. To change a parameter in the model between runs, for example having the valve opened instead of shut, we simply edit its value in the variable browser, and press the Simulate button. We observe that the mass flow and pressure drop have changed from the previous run. To plot both variables, simply keep the two boxes simultaneously checked.